So if you were to consider the elastic bending of beams, you have in Appendix B3 this kind of a summary of various loading conditions fixed at one end as a cantilever with a deflection that has to be accounted for based on a load at the end or a distributed load, a torque moment. You could have like a slider on one side. You could have a distributed load over here. It could be fixed at both ends as a beam, and then you could have a load in the middle or a distributed load. So a lot of different possibilities. Okay. And then accordingly, the value of C1 and C2 in these equations would change. So in our particular case, C1 for a square beam, what is it? Then what is I in this particular situation? I depends upon the cross-sectional geometry as can be seen in all these different combinations. For a rectangular cross-sectional beam, it's B is the width and H is the height. It's BH cubed divided by 12. Alternatively, if the width is given by W and T is the thickness, then WT cubed divided by 12 would be the way you get the moment term, which is listed in Appendix P2 of the 4th edition. Let us apply this set of equation where you have the mass of the material expressed as a performance index as a product of the functional requirement, the geometric requirement, and the material index. So if M1 is given by this and M2 is given by, right, two materials, right? So mainly M1 would have properties based on one material. Let's say its density is ρ1 and its modulus is E1. Let's, in contrast, look for the overall mass when another material is chosen with a density ρ2 and a modulus E2. So what is the mass of a beam made of the second material relative to the mass of the beam made by the first material for the same geometric and functional parameters? Okay, so this becomes a constant. So basically what you end up having is M2 by M1 is a ratio of capital M1 by capital M2. So the mass of the material that you want to decide as a new material to change the original can be determined by taking an inverse proportionality of the material indices. Right? Material index of the first material divided by the material index of the second material. So for a given shape, the reduction in mass at constant bending stiffness is given by the ratio of material indices. Same thing applies to bending strength also. Let's put all these possibilities into practice. Here is an overall scenario where you initially have a steel component and you're dealing with elastic bending. It could be a tie rod, it could be a beam, it could be a panel. Now steel has a modulus 210 and a density of 7.8. Aluminum, if that was going to be something you were choosing to replace, has a modulus of 75 and a density of 2.7. Magnesium is the lightest of all. It has a density of 1.7. It's also the weakest of all. It has a modulus of 44 gigapascals. So for a tie rod, what is the material index? For a beam, what is the material index? For a panel, what is the material index? So the material index for a tie rod is E divided by rho. So 210 divided by 7.8, which is roughly 27. 75 divided by 2.7 for the tie rod, about 27 again. 44 divided by 1.7, 26. So very close to 27. So you see, for a tie rod, it really does not care which of these three materials it's built off. The function is pretty much the same. It's dominated by pretty much the E by rho ratio. If from a tie rod you went to a beam, what happens is you're looking for a material index of E raised to half divided by rho. So if you take the square root of 210 and divide it by 7.8, you will now get a material index of 1.86. You take the square root of 75 and divide it by rho, you get 3.21. You take a square root of 44 in a similar manner, divide by rho, you get 3.9. Try these out. Okay, I'll add an Excel spreadsheet for you to verify, but try it out by calculator, pen and pad, write it out so that you can compute material indices for various materials. Similarly, when the material index is e raised to 1 by 3, how do you get these numbers? Take a look. More importantly, take a look at if you are taking the same geometry and just making a component of exactly the same attributes. So the volume is the same, but now you just change the density. So if you replace steel, right, that assume that was the volume of it was 1 meter cubed. If you now replace that same component with the same dimensions with aluminum, since it's about roughly 1/3, you'll have a, a, a material index of 0.35. This is a conventional way people thought of just making something lighter. Alternatively, if you use magnesium, it's about 1/4 of that, and so 0.22. Now, here are the trends that you end up seeing. Based on the E by rho material index for a tie rod, it really does not matter whether you swap it from steel to aluminum or magnesium. Your performance is not going to get compromised. However, if you now go to a beam or a panel, it turns out that if you go to an aluminum or a magnesium, the material index actually increases, and for the same scenario, you actually have a higher performing by swapping it out. So you can minimize the mass more effectively by going to magnesium. That's pretty much what. See, on contrast, if you just take the same geometry and replace it by aluminum, you end up actually decreasing, okay, rather than increasing the performance. That means you are going to, for same geometry, if you end up replacing aluminum magnesium, you're going to make a structurally poorer material. So if you take the material indices and now go to the scenario of what is the mass that's going to be there, right? The minimum mass required to meet the constraints for delivering on the given function. So the objective being minimizing the mass. Right? Let us see if it is actually possible to do so effectively without violating the constraint or failing to deliver on the function. M2 by M1 is equal to capital M1, which is the material index, divided by capital M2. So all the different M's were computed in the previous table over here. What do you see? So for the various material indices, what you end up seeing is, because the material index is relatively the same, to replace a tie rod made out of steel, which has 10 kilogram force mass, basically, if you made something out of aluminum or magnesium that delivers on the function and meets the constraints, roughly you really have no weight savings. They are all about the same. However, if you built a beam now that was originally from steel and weighed about 10 kilogram force, then what that means, based on this ratio over here of M1 divided by M2, okay, which is about roughly 0.6, and M1 over M2, which is roughly about 0.5. What you end up having is, you end up having the mass to be about, compared to 10 kilogram force, to be about 6 kilogram force, or 4.8. So you can actually be able to, in a similar manner, if you go to the third criterion, I leave it as an exercise for you to figure it out for the panel based on using M2 by M1. So the new mass compared to the original mass of steel, what is it relative to the old material index divided by the new material index for the replacement. It turns out that as you go from working with a tie rod, which is relatively insensitive to the three different materials, if you go to a beam or a panel, you can actually make a much lighter component as a beam or a panel when you make it out of aluminum or magnesium compared to that of steel. What happens is, if you go with an equal volume, you end up with a material index of 3.5 or 2.2. So these would actually not be very useful compared to, they'd be lighter for sure, but they would fail to meet one of the criteria. Okay, and so it will fail prematurely. Think over this issue